Today I am gonna talk about the difference between bias and variance and also the trade-off between them. I am gonna use a simple example here. That is the experiment that scientists made on mice. So imagine we measure the weight and the height of a bunch of mice, and then we plotted the data on a graph. That's what I have done here. Right, I got the scatter plot here. So what that turns out is light mice, right? It tends to be shorter. Okay, right, and the fatter or the heavier mice, they tend to be taller. Okay, that's what I figured out. But after a certain weight, mice, they don't get any taller. Did you see that? Okay, they just gain the weight, but they don't grow taller. So what I would like to predict is I will be giving a mouse weight, and I will tell what is the mouse height. Okay, so ideally, what I need is a specific or the exact mathematical formula that can describe the relationship between the weight and the height. Okay, it might look like this. Okay, so okay, no, I don't think it's a good draw. So it will be, it look like this curved line, right? So when you ask me, oh, what is the weight? Okay, what I can do is I just follow the formula and I go grab the height. And I will tell you, oh, this is the height for this mouse. Right. Okay. But in this case, I don't know. I don't know about the formula. So what I'm going to do, and I am going to use two machine learning methods to approximate this relationship. But however, I will leave the true relationship, so which is the curve here, I will leave that in the figure for reference. Okay. Okay, the first thing I'm gonna do. Okay, so in the previous lesson, we know that the first step is to split the data. Okay, we'll split the data into two sets. One for training the machine learning algorithm and one for testing data. Okay, so I'm gonna use a different color here. Okay, this one color here. I will label the dots in blue to make that as training set, and I will leave the black ones as testing data. So in Python that we have the did I select the layer? Okay. I feel like it's hard for me to label the black dots. How can I? Oh, I should set up the layer first. Sorry. Okay. Let's try again. Now looks good. Yeah. So what I'm doing is I label the training set, the training data as blue. But in Python, right? In Python, it will be the Python will automatically by using the scikit library, it will do the split for you. You just tell Python what's the portion of data that you think about. Maybe 40% will goes to training, or goes to testing data, and usually it's 30%, right? So they will randomly select those data sets for you. But now I'm just assume, okay? Just assume what I'm doing here is I randomly select some training set and randomly select some testing set. oops, where did my curve go? Well, I think I just deleted my curve. Okay, let me draw the curve again. Right, so this is my reference. Remember that, right? This is my reference. Let me lock this layer. Okay. So here, the blue ones, these are the what? The training set. Okay, so the first machine learning algorithm that I'm going to use here is the linear regression, aka least squares. Okay, so let me put this on that. Do I have a line tool? Okay, never mind. Okay, so it will look like this. And you know that the linear regression, it fits a straight line to the training set. But wait, the straight line, it doesn't have the flexibility. For what? It cannot accurately replicate the true arc in a true relationship, which is the curve, right? So no matter how hard I try pretty hard to fit the line, it will never curve. Okay, so the straight line will never capture the true relationship between the weight and the height, no matter how well I fit it into the training set. This is called bias. So what is the definition of bias? Okay, it is the, I'll write it here. Okay, give me some space. Okay. The inability for a machine learning method. So in this case, it's linear regression, right? To capture the true relationship is called bias. Okay, that's the inability for a machine learning method to capture the true relationship. It's called bias. Okay, that's the definition for bias. Because the straight line, it cannot be curved like what is the true relationship is. It has a relatively large amount of bias, right? Okay, so now let me try another machine learning method. Let's fit a squiggly line to the training set. Okay, so let me cancel this out. Okay, so for a squiggly line, use another color, be pink. Okay. Oops, I just cleared the blue points. Oops. Do you remember I do have those blue points, as I said, will be randomly selected as the training set, and now I just okay. So now I just labeled the training set as pink. Sorry, guys. Okay, so what I'm gonna do is I'm gonna use the second method to fit a squiggly line. Okay, it will be look like this. The squiggly line is super flexible. So it goes through the training set along the arc of the true relationship. So because the squiggly line can handle the arc in a true relationship between weight and height. does it have a high bias or does it have a low bias? It can fit pretty well. So it has very little bias, right? So we compare, so what we can do, we can compare how well the straight line and the squiggly line fit the training set by calculating what? Their sum of squares. So in other words, we measure the distance from the fit lines to the data and we square them and add them up. Okay, so do you remember for the linear regression, right? We got a straight line. I think I'm gonna redo that. I'm so sorry. Okay, remember this was the line, right? Okay, so we measure the difference from the fit line to the data. Okay, this is my prediction. The red line, right, is my prediction. Okay, what's the distance? Okay. Oh, let me label the training set here. Okay, so will be the real data to my prediction. Okay, so the distance will be look like this. This is the distance for linear regression. But for the squiggly line, do you see that? What's the distance? Will be 0. Okay, will be 0. Do you see how the squiggly line, it fits the data so well? Right, so the distances between the line and the data are all 0. So in this case, the straight line, it fits the data set. Is that better than the squiggly line or not? So in this case, I will see the winner for this case will be squiggly line, right? But remember, so far what we have done, we just calculated the sum of squares for the training set. We still have the test set left. Okay, now it's time for us to calculate the sum of squares for the testing set. Okay, let's go back to the straight line here. Okay, and you know that the black points are my testing set, right? So what will be the distance? Okay, use another color here. How about just use black? Okay. This is for the straight line. I would say it will probably look pretty similar to the previous one, or pretty similar to the training set, right? But how about the squiggly line? Okay, now you see the difference. We used to have zero on the distance, but now this time I would say the straight line wins. So even though the squiggly line, it did a great job fitting, but it's on the training set. Okay, but how about the testing data? So in machine learning, the difference in fits between data sets is called variance. Let me write this down. So the difference in fits between data sets is called variance. Okay, that's the definition for variance. The squiggly line, right, this one, it has low bias because it is pretty flexible. It can adapt to the curve in a relationship between weight and height. But the straight line has very high variability because it results in vastly different sums of squares for different data sets. Right? You can see that. You can see that from the graph. You see the pink dots here on my training data set. Oh, in this straight line, it fits everything. Okay, but the testing data not. But on the opposite, the straight line, it has relatively high bias because what? It cannot capture the curve in the relationship between weight and height, right? But the straight lines has relatively low variance. Why? Because the sum of squares are very similar for different data sets. So in other words, the straight line might only give good predictions, not great predictions, but they will be consistently good predictions. Okay. Now I'll give you a terminology. Okay. So because the squiggly line, it fits the training set very well, but not the testing set, we say that squiggly line is overfit. Now you know what does overfit mean, right? Okay, so in machine learning, the ideal algorithm has low bias and can accurately model the true relationship. So as you may know, it will be you see the reference line, the light blue one, that is a good prediction. That is a good model. Why? Because it has low variability by producing consistent predictions across different data sets. And also, as I said, the low bias. So low bias and low variability, then you will have a good model. Okay, so to have a good model, we'll need to find the trade-off, or say the trade-off between a simple model and a complex model. The simple model here in this case is the straight line, and the complex model is of course the squiggly line. Okay, so this is what is bias, what is variance, and what is the trade-off between them. You always have to do that when you train a model. Always consider about the trade-off between bias and variance. Okay, so I will see you in next class.